3 minutes. Mark.
Dumping LN2, starting flight pressurization.
All meters are covered.
How the tanks look, Jack?
Look good.
Vertical start.
First phase.
Minus 10 seconds.
In the middle of the 20th century, for the first time in history, man reached beyond his planet and began to probe the mysteries of space. Is one of the tools with which man is creating a new age. But the age of space is also the latest chapter in a story as old as man himself. According to myth, Alexander the Great tried for the moon. He used griffins, which flew upward to catch a sheep's carcass, kept always out of reach. An 18th century adventurer thought he could use willpower to get to outer space. A French balloon designer provided everything the space traveler could desire. Jules Verne, more mindful of the laws of nature, conceived of a monstrous cannon and a moonship carrying 3 men and 2 dogs. According to his story, one of the dogs died and was cast into space, where he went into orbit. Less than 100 years later, the dog Laika was carried into orbit by a Soviet satellite. 2 monkeys, Abel and Baker, traveled 300 miles out into space and back in the nose cone of an American rocket. And man himself got ready to follow. Man first developed sounding rockets that gave him new insights into the upper atmosphere. These tools opened a window in the masking layers of the lower atmosphere, and through this window, man caught glimpses of the true nature of the particles, radiations, and forces in near space. Although a sounding rocket radios back a profile of the atmosphere, its flight is over in 10 minutes or less. Man needs more than this. He needs first-hand data from near space and beyond, reporting events and changes over long periods of time and wide stretches of space. Today, satellites can stay in outer space and report continuously on a wide variety of phenomena, from cloud cover and the Earth's magnetic field to radiations and particles from the sun and beyond. According to their objectives, satellites come in many sizes and shapes. How do they function? First of all, to reach space, a satellite depends on a rocket system more powerful than ordinary sounding rockets. This system must include guidance or navigation equipment to direct it on a predetermined course. The vehicle usually consists of more than one rocket or stage. Most of its weight is taken up by propellants, both fuel and oxidizer. Launching is not an easy task. In the countdown, each step must be scheduled exactly, checked and rechecked. Still, there are no guarantees. man's greatest pioneering effort, his advance into space, there are inevitable problems and agonizing trials. But one by one, problems give way to solutions. In the first 2 years of the space age, 20 scientific satellites and space probes were launched successfully, 6 Russian and 14 American. The most precious component of a space vehicle is its payload, the satellite itself. Here are the electronic eyes and ears, the brains and voice that measure and report temperature, composition, and structure of space. These instruments, skillfully miniaturized, provide scientists with observations hundreds and thousands of miles beyond our planet. One of the important elements of this instrument package is an 8-ounce tape recorder. It stores the data collected by the satellite's measuring devices and plays it back quickly on command from a ground station. Either on command or continuously, the collected information is broadcast back to Earth by tiny transmitters. Various combinations of instruments are assembled depending on the scientific objectives. Components are installed as compactly as possible. Space, like weight, is a critical factor. To place each pound of satellite into orbit, hundreds of pounds of rocket may be needed. This satellite's magnesium shell provides maximum strength with minimum weight. Several thin metallic coatings, including pure gold, help maintain the proper internal temperature range while the satellite is in orbit. Each satellite has its own special features. On Sputnik 3, for example, metal flaps open and close to control temperature. On other satellites, such as Explorer 3, reflecting oxide stripes maintain the average inside temperature between reasonable limits, 30 and 100 degrees Fahrenheit. Although the sun creates a heat problem, it also acts as a source of power. Solar cells, as on the paddles of Explorer 6, convert sunlight into electricity, recharging the satellite's batteries. Laboratory tests help to ensure that the payload will withstand not only the intense vibration of launching and flight, but also in some cases, the strain caused by spinning hundreds of revolutions a minute. Other tests ensure that the rocket's nose will open up and fall away, so that the satellite can be separated from the rocket system. Finally, all is ready. How is the satellite placed in orbit? Why does it stay there? Although there are many vehicle-satellite combinations, the Vanguard offers a good example of basic technique. 72 feet long, as tall as a 7-story building, the 3-stage rocket takes off, bearing the satellite. Its path has been set before launching. Guidance equipment in the 2nd stage keeps it on course. About 2 minutes after launching, nearly 40 miles above the Earth, the 1st stage burns out, falling into the sea as the 2nd stage fires. The rocket continues along a curved path. It is now climbing through such thin air that shielding from air friction is unnecessary. The nose cone is jettisoned. Nearly 5 minutes after launch, 140 miles out, the 2nd stage burns out. The rocket coasts on to a height of about 300 miles. At this point, it is traveling parallel to the Earth's surface. However, the vehicle is traveling only 9,000 miles an hour, not yet fast enough to overcome the pull of gravity and stay in orbit. Inside the 2nd stage, the 3rd stage, containing the satellite, now begins to play its part. Small rockets start its spinning on a turntable. When the spinning reaches 150 revolutions per minute, the second stage is separated, its job completed. Stabilized by its spin, the third stage fires and gathers speed. Then it too burns out and ejects the satellite into orbit at 18,000 miles per hour. The speed at which the satellite's movement forward matches its fall toward Earth and thus keeps it in orbit. 300 miles out, beyond the dragging effect of the lower atmosphere, it continues to move at its original orbital velocity. Depending on their orbits, some satellites circle the Earth about once every 90 minutes. Others may take hours more. Satellite orbits, like those of the planets, are elliptical, with a far point, the apogee, and a near point, the perigee. After many such orbits, most satellites encounter enough atmospheric drag at perigee to slow them up a little. This drag eventually causes them to plunge into denser atmosphere and be burned up by friction. With a high enough perigee, some satellites will remain in space virtually forever. Vanguard 1, launched in 1958, achieved an initial perigee of 409 miles and an apogee of 2,465 miles. It may stay up for hundreds of years. Looking for a satellite is almost like dragging the Pacific for a golf ball. Some of them can be seen by the naked eye or with binoculars, but only around twilight. However, scientists have developed systems far more powerful and precise than the eye to follow space laboratories and to communicate with them. Special radio devices track a satellite by measuring the direction from which its radio signals come. From successive angles of direction, the satellite's orbit can be computed.
How's she look, Freddie?
Amateur radio operators also pick up and report the satellite signals. Radio tracking networks stretch around the world. Another international network consists of optical observation stations, manned by volunteer teams engaged in Operation Moonwatch. Using telescopes, these observers are especially helpful in finding a newly launched satellite and in following a dying satellite in its final variable course. Each observer is assigned his own sector of sky. Upon sighting the satellite, the observer, such as this member of a Philippine team, calls out,
In, time, out.
A series of Moonwatch reports, coordinated with a recorded time signal, helps in plotting the path of the satellite. Photographed by a Moonwatch observer in Schenectady, New York, this actual fast motion shot shows the tumbling third stage rocket of Sputnik 1 crossing the sky in front of the moon. The most precise tracking system is the international chain of optical observation stations equipped with specially designed cameras. A dozen of these were stationed around the world during the International Geophysical Year. Taken by one of these cameras, this photograph, with its dark and light elements reversed for clarity, shows the track of Sputnik 3 against a background of stars. Here the aim of the camera was fixed, and the satellite track registered as an intermittent line showing camera time marks. The camera can also follow a satellite. The resulting photograph shows it as a point, in this example Vanguard 2, with the various planets and stars appearing as lines. A series of these photographic records provides an accuracy of satellite position within 1/1800th of a degree in space and 1/1000th of a second in time. Orbital data are sent to computing centers, which process the observations and reduce them to a mathematical description of the satellite's past history and present orbit. Here, too, predictions are made as to the satellite's future course. What about the information obtained through satellites? In the first few years after the earliest successful launching, a number of unexpected but very significant findings were made. Two of these were made possible by precision tracking. The first finding, interpreted from tracking data of Vanguard 1, provided new facts about the shape of the Earth, facts that could be obtained only from a satellite. Minute differences in the repeated measurements of Vanguard 1's orbit led scientists to believe that the Earth's gravitational effect on the satellite varied in certain areas, and thus the distribution of the Earth's mass must vary. These variations caused scientists to change their concept of the Earth's shape. Greatly exaggerated here, the differences between the old outline and the new, slightly pear-shaped one are actually no more than about 50 feet in certain places. But this refinement, however small, is of great importance to a better understanding of the nature of the Earth's crust and interior. A second major finding was obtained from studying the slowing down of Vanguard 1, caused by atmospheric drag. This graph indicates how the drag on the satellite increased substantially following flares on the sun. This finding led to a new theory. Charged particles streaming toward Earth after solar flares increase atmospheric density enough to affect a satellite's orbit. Satellite tracking data provide information about another factor nearer Earth, the atmospheric density which ultimately destroys them. By studying the decline of a satellite's orbit as air drag slows it up, scientists compute atmospheric density at many levels. Analysis of such data has established that at heights of 200 to 400 miles, air density is at least 10 times greater than was estimated in the days before satellites. In addition to the information that they can deduce from observing satellite orbits, scientists obtain much direct data by listening to the instruments carried aboard the satellite itself. Signals from satellite instruments are received as a kind of electronic shorthand or code. The various signals are identified by changes in their length, in the time intervals between them, and in their frequency. These messages are recorded on the ground in permanent form for later analysis. This technique is known as telemetry. For instance, a special metal strip on the satellite surface and a microphone inside record out in space the erosion and the impact caused by tiny particles of dust known as micrometeorites. From telemetered reports of this bombardment, it has been estimated that as much as 10,000 tons of these particles enter the Earth's atmosphere every day. Micrometeorites are so minute, they are no appreciable hazard for space vehicles. Satellites not only look out into space, they also look down on the Earth and can provide meteorologists with worldwide coverage of cloud formations. This is the first weather image ever transmitted from a satellite. Recorded by a scanning device in Explorer 6, orbiting 17,000 miles above Earth. It indicated cloud cover over a broad area in the Central Pacific. This technique will permit man to track and predict the movement of great destructive storms. Satellites also tell man about strange forces and events in space. They measure the Earth's invisible magnetic field, whose lines of force reach out tens of thousands of miles in giant arcs. They detect ultraviolet light and X-rays, which are almost completely absorbed in the middle layers of the atmosphere. They record primary cosmic rays streaming from space and occasionally from the sun. These so-called rays are actually atomic particles which travel at very great speeds. High in the atmosphere, they collide with atoms and molecules of gas, thereby creating secondary cosmic rays which penetrate the atmosphere and can be recorded on or near the Earth's surface. But to investigate the primary rays directly, scientists must send their instruments high above the atmosphere. Satellites provide an especially good means of keeping the instruments up there for long periods. In the course of probing cosmic rays, American satellites made possible the most significant finding of the space age, the discovery of the vast and complex regions called the Van Allen radiation belts. Below about 400 miles, the first and third American satellites found the amount of cosmic radiation that scientists expected. But farther out, the satellites found radiation so intense that their Geiger counters were temporarily saturated. Measurements by a later satellite showed no tapering off as far out as 1,400 miles. Instead, the radiation seemed to double in intensity every 60 miles of altitude. Late in 1958, space probe Pioneer 3 reached out 66,000 miles and recorded two peaks in radiation intensity, one at 2,000 and another at 10,000 miles. Pioneer 3 also traced out the outer region of the radiation. These findings led scientists to believe that two great zones of radiation encircled the Earth under the influence of the Earth's magnetic field. Space probe Pioneer 4 confirmed these findings and recorded fluctuations in the farthest regions of the outer zone. Scientists believe that the outer radiation zone consists of electrically charged particles ejected by the sun. Streaming through space, these particles are trapped in the Earth's magnetic field. The inner zone is generally believed to be created by cosmic rays bombarding the Earth's atmosphere. In this bombardment, high-energy neutrons are created low in the atmosphere. Some of them travel rapidly to high altitudes where they change spontaneously into charged particles. These particles are then trapped in the Earth's magnetic field. New details are being added to the picture of this highly complex region that surrounds our planet. Its discovery is a most important step in sounding the endless sea of space. Space probes are reaching out beyond the Van Allen belts. They have reached the moon and encircled it. The third Soviet space probe produced this photograph of the hidden far side of the moon. In placing a satellite in orbit around the moon, three major motions going on simultaneously must be taken into account. The Earth's spin on its axis, the orbit of the moon around the Earth, and the orbit of Earth and moon together around the sun. Variations in the angle between the moon's orbital plane and the Earth's axis must also be considered. All these factors complicate the task of traversing 250,000 miles from Earth to moon. A lunar rocket needs enough velocity to carry the vehicle beyond the pull of Earth's gravity in the direction of the moon. Even after the probe escapes from the Earth, the moon is still 2 days away. The last stage slows up by retro-rocket burst. The moon's gravitational field sweeps it up. The satellite acts as a watchful reporter, sending back new data about the moon's composition, its size and its mass, and the radiations and particles near it. This is Earth in the mid-20th century. Most of us remember when the moon was its only companion. But since October 4th, 1957, when Sputnik 1 went into orbit, the Earth's community has been growing. Now there are several companions, watching, listening, recording, increasing man's knowledge day by day. Tomorrow's satellite will be an even greater tool for science. Satellites will give meteorologists round-the-clock reports on worldwide cloud patterns and trends, thus allowing more accurate and complete weather forecasts. Satellites will relay man's radio signals, greatly improving his worldwide communication networks. Satellites and probes will help astronomers find answers to questions about our neighbors in the solar system. Deep probes near the sun will give earthbound solar physicists more information about the incredibly hot, electrically charged atmosphere of our nearest star. As for the day after tomorrow, satellites and probes may bring man closer to stars far beyond our sun. Within our framework of time and space, journeys by man himself beyond our solar system are still inconceivable. But through his scientific instruments, carried by deep space probes far beyond his own limits, man can reap new knowledge of distant stars and galaxies. Science in space helps man understand more and more that planet Earth and the solar system are only specks in a vast cosmos. There may be other forms of matter and energy, other kinds of worlds, even other forms of living things. Man's spirit is his most powerful drive. In the words of the Norwegian scientist Fridtjof Nansen, the history of the human race is a continual struggle from darkness toward light. It is therefore to no purpose to discuss the use of knowledge. Man wants to know, and when he ceases to do so, he is no longer man.